So this is where we left off last time. Let me make a couple of comments here. Now, we divided by x to get this special multiplier to eliminate the a. And so whenever you want to divide by something you don't actually know the value of, you got to make sure you handle the possibility that it would be 0. Well, if it were 0, I can't do that. What does that say about the property? Does the property still work? Well, if x were 0, then we would have a row of zeros in the first row, and then a previous property tells us that the determinant is 0. And of course the product of the diagonal entries would be 0, so that matches. Okay, well then suppose x is not 0 and y is 0. Then I could do this step, and I could do this step. But then if y were 0, I would get a row of zeros right here. Okay? And then the determinant would be 0, and so the property works. If x and y are both non-zero, so we could go all the way to here. If x and y are not 0 but z is 0, then the determinant is 0 according to this expression, and that still matches because we would have a row of zeros in the last position. Okay? So that's great. And well, actually I couldn't even get here, could I? Because I couldn't factor out a 0 here. So maybe here at this point I would stop and say, okay, I have a row of zeros. Alright, so we're going to use some of the same reasoning here to prove property 8. Property 8 says that if a matrix is singular, then its determinant is 0. If it's not singular, so if it's invertible, then the determinant is not 0. So let's think about how to prove this. Well, let's assume the case that it's invertible, and we'll show the determinant is not 0, and then we'll handle the other case. So let me just write a general matrix. I'm just going to put dots here. I don't really care what these numbers are, and I'm not even going to do much with it. If we were to follow a process like we did above, then if the matrix is not invertible, then we know we can go through a sequence of row operations and get to the row echelon form, which is a lower triangular matrix, and that wouldn't change these values, these dots that I'm putting here. It wouldn't change anything. And so if this involved factoring things out, then I would just have a multiplier here. And of course the things I factor out are non-zero. And the point is, if I can get to a row echelon form that looks like this, then k is non-zero, this determinant is 1, and so the determinant would not be 0, and that's it. So that's a pretty simple argument. Now what if the matrix were singular? Where if the matrix were singular, if I take that 3 by 3 general matrix, then we know that if you have a singular matrix and you do row reduction, and if we have to factor things out to get ones, we could do that, but you see, we would get a row of zeros. If a matrix is singular, then the row echelon form contains a row of zeros. And so we know that if we have a row of zeros, then the determinant is 0. So that kind of shows the property just by making row echelon form arguments. Now, another way to say this property is just to say that a matrix is invertible if and only if its determinant is not 0. So it kind of goes both ways. Now here we have a simple consequence of this, that the determinant is plus or minus the product of its pivots. Okay, so let's go back up here to a calculation we did earlier, and let me remind you what pivots are. The pivots are the numbers you use to build a multiplier. So here, this is the multiplier we needed from row 1 to eliminate a. And the pivot in this case is x. Okay, and here y is used, okay, to eliminate h to build this multiplier to eliminate h, and so that y is another pivot. Okay, so the pivot is basically in row reduction. After producing a lower triangular matrix, it's the first non-zero element of that row. So z is another pivot. And so an interesting way to look at this is that we got a product of pivots as our determinant. This is actually generally true. The determinant is always the product of the pivots if it's invertible. Now, we didn't have to do any row interchanges here. If we did any row interchanges, then we would have to put a plus or minus in front of the product of the pivots if we moved the rows. And so a consequence of this is that the determinant of a matrix that is invertible is the plus or minus the product of its pivots.